Good day, everyone. Welcome to another lecture in the series Organic Chemistry 1. And today we'll be focusing mainly on reactive intermediates, particularly carbanions and carbocations. And of course, my name is April Johnson. So, as you know already, carbanions are negatively charged and carbocations are positively charged, and they are reactive intermediates and they have very short lifetimes. They are generated during the course of organic reactions. So this I'm sure you know already. And in contrast, radicals are uncharged reactive intermediary species. So just in case you might be wondering why we say carbanion, just to break it down a little bit further, it's carbon, right? So we have carbon here, and it's an anion, negatively charged, so we just say carbanion for short. So just some more details in terms of the structure and geometry of carbanions. So they contain an unshared pair of electrons, as we see here, as well as here, on a trivalent carbon atom. They are generally, the carbon that is generally sp3 hybridized, and so we have the geometry here of trigonal pyramidal, right? So we have the carbon in the center. X represents any of the bonds, anything that is bonded to, and then we have the unshared pair of electrons there. All right, so you might be wondering, how are they generated? They can be formed via, different mechanisms. However, what we'll be looking at here is how they form from organometallic reagents. So you might be familiar with your alkyl lithiums, designated R, Li, lithium, and R, of course, represents any alkyl group. And you should be very familiar with their Grignard reagents of the formula RMGX. So X represents any halogen, and R, of course, alkyl group. And then finally, your lithium dialkyl cuprates, formula LiCu, so lithium, copper, and the same R group. So you generally have the same R group twice. And of course, R represents an alkyl. So this is the mechanism in which the carbanion is generated. So we start off here at this bond, and the arrow starts on the bond and it ends on the R, which is the alkyl group. And so we end up with a carbanion and the metal that is positively charged. In other cases, carbanions can be formed when protons are removed from carbon atoms in a molecule. So we have seen that before. So you have a carbonyl and you have an acidic proton beside it. A base can pull it to form a carbonyl. So that is one other way. And of course, for these types of reactions, we know that the metal is more electropositive than the carbon, and so we have a polar bond, which is susceptible to being broken, and so we end up with our carbanion here. So generally, carbon-hydrogen bonds are not polarized, so the hydrogens exhibit low or very low acidity. However, when the carbon atom is substituted with a strong electron withdrawing group, right, formation of the carbanion is favored. So this is because the anion generators is stabilized by induction and sometimes by resonance. So if you'd recall, this is the direction of the electron movement, right? So this arrow is showing induction. So because Z is electron withdrawing, then it will pull electrons to itself and therefore weaken this carbon hydrogen bond, which doesn't usually we wouldn't consider it to be acidic, meaning we wouldn't expect this hydrogen to be liberated easily, right? But because it's attached to something that is pulling electrons to itself, right? Then a base can come in and pull it, because it's now, this carbon hydrogen bond, as I said before, is now weakened, and so the base can pull the proton to form the carbanion. So follow the arrow movement. The pink arrow is not a resonance arrow, it's just showing induction, which is showing the movement of electron, that the electron withdrawing group here is pulling electrons to itself. That's what the pink arrow is showing. The blue arrow is a resonance arrow, so the base is pulling this proton, this carbon hydrogen bond is broken, and the pair of electrons will now reside on the carbon, which is why you now have a carbanion. Just to reinforce here that in terms of the stability of carbanions, they are stabilized by the presence of neighboring electron withdrawing groups, as we just saw. However, they are destabilized by electron donating groups. And for the next slide, you will need to remember that when you see EWG, we're referring to electron withdrawing groups, and EDG, we're referring to electron donating groups. Right, so here we have an image of induction versus resonance. So here we have our carbanion, right? And because this group is electron withdrawing, it will pull electrons to itself and therefore stabilize our carbanion, right? And it can also be stabilized by a resonance. And as we have seen in previous lectures, we understand that resonance has to do with delocalization of electrons. So this pair of electrons here on the carbon, which forms the carbanion, is delocated across these two bonds, right? So we're able to see two resonance structures or canonical forms here, right? So here we're showing how electron withdrawing groups here are stabilizing our carbanion via induction as well as resonance. So at this point, you might be wondering, what are some other electron withdrawing groups? So here we have seen, the nitro group, etc., right? But there are several others. So here, for the electron withdrawing group, they are deactivating. So all of these compounds that fall in this category are electron withdrawing. So we have our nitro group here that we just saw on the previous slide, right? And these are electron donating groups. And as you can see, electrons, right? So you can see the lone pairs on the nitrogen, the lone pairs on the oxygen, and other species. So they are very activating and they're always donating electrons, while the electron withdrawers, they are pulling electrons to themselves, right? So that is the distinction. And you need to have an idea of what types of groups are electron withdrawing, what category of groups are electron donating. So you will be able to know if a particular carbanion is stabilized or not. How likely will it form if it has an electron withdrawing group versus an electron donating group? And you won't know that if you don't know the groups and which category they fall into. So that leads us now to question 1, which is, what is the hybridization of carbanions? And B says, what is the molecular geometry of carbanions? So the answer is they're generally sp3 hybridized, and for the molecular geometry, they are trigonal pyramidal. So as we said before, the carbon in the center generally bonded to 3 things, and then we have the lone pair. All right, so your follow-up question 1 is, give 2 examples of electron withdrawing groups and 2 examples also of electron donating groups. So before you go back, just try to recall, some of these questions you should try to recall so that you can, start the process of remembering. All right, so now we're going to look at reactivity of these carbanions. So as we probably would have seen or known, carbanions are both bases and nucleophiles. They're electron rich, so that shouldn't surprise you. As nucleophiles, they react readily with a carbon bearing a good leaving group, and we'll see some examples in a little bit. This is used synthetically to generate new carbon-carbon bonds. So you guys will see that this carbanion is a very important intermediate, and we'll see some reactions in which it participates in. So the first one we're looking at is reaction with alkyl halides. So again, it's a nucleophile, right? So it's always looking for electrons, right? So we have the negatively charged anion here, carbanion, and then it will attack the electrophilic carbon of our alkyl halide. So remember, this bond is now polarized because X represents some halide that is pulling electrons to itself, and therefore polarizing this bond, making the carbon electrophilic, right? And so the carbanion will attack the electrophilic center, causing the carbon halogen bond to break. So the arrow starts on the line and ends on the halogen, which is why we have a negatively charged halogen here, and we now have a new carbon-carbon bond, right? So as we mentioned just a while ago, the carbanions are very important in forming new carbon-carbon bonds, which we can see here. Another way in which they react is with carbonyl compounds, right? So as we can see here, or carbanion, which we see being nucleophilic again, it will attack our electrophilic center of our carbonyls. So we're talking about this might be a ketone, right? If these two R's are carbons, right? So the carbanion will attack to our electrophilic carbon center here, as we see with the arrow. And then for the second arrow, the arrow starts on the line and ends on the oxygen, right? So as we said before, follow the arrow to follow the electrons, right? And so here again, we have a new carbon-carbon bond forming, right? And then our carbon-oxygen bond, one of them would have broken, and the electrons now reside on the oxygen, which is why we'll have a negatively charged oxygen. So this oxide is now able to pull a proton from whatever is in the medium that can offer a proton, and so we end up with an alcohol, right? So we can start off with a carbanion reacted with a carbonyl and end up with a alcohol. So again, a new carbon-carbon bond can be formed as a result of carbanions reacting with carbonyl compounds. All right, so we have some other examples, right? So here we have a carboxylic acid derivative. So X here, a lot of the times when you see X, you know it represents a halogen, right? So we have our carbanion here. It will attack our electrophilic center. As we know, this bond is polarized by virtue of, our electronegative oxygen here pulling electrons to itself, polarizing this carbon oxygen bond, leaving our carbon here being delta positive and therefore electrophilic, right? So this carbanion will attack our electrophilic center, causing this carbon oxygen bond to break, and the electron will now reside on the oxygen as we have seen before, right? So the only difference here is that once the pair of electrons can reform or carbon oxygen bond, double bond that is, and then cause or halogen to be eliminated, right? Or cause us to lose our halogen here. And so we have again a new carbon-carbon bond being formed, right? So again, we follow our electrons and we follow the arrow to understand the movement of electrons. So again, we have our carbanion and we have a new carbon-carbon bond forming, and we end up here with a new carbon-carbon bond, right? Another example here is that they can also react with epoxides or oxiranes, right? So epoxides is a 3-membered ring. So we have carbon-carbon and we have a 3-membered ring to an oxygen, right? So our carbanion can attack our carbon here, causing our carbon-oxygen bond to break, right? So as is evidenced by the arrow starting on the line and ended on the oxygen, right? So this carbon-oxygen bond is broken, so we can see a ring opening here. And, just to note that this ring is susceptible to this reaction because it is a strained ring, right? And so once this intermediate is formed, our oxide is now able to pull a proton, and so we end up with, again, a new carbon-carbon bond and an alcohol in this case, right? So just to point out here that, if you are given a product and you know that you start off with a carbanion, then you should be able to predict the other reactant. Let me say that again. If, let's say, in a question you're given the carbanion, or, not necessarily the carbanion, but the reagent from which you would get the carbanion, and you are given just that and the product, right? You should be able to identify the new carbon-carbon bond and therefore figure out what it reacted with, right? So if you're not good at that at this stage, then that is something that we will build on as we go along, right? To look at the product, look at one of the reactants and identify the other reactant. All right, so let's look at question 2, right, which will give us an idea of what I'm talking about, just in case you have no clue. So question 2 says, suggest reagents and conditions as well as a mechanism for the following reaction. So here, and I hope that you pause the video and try to answer it before you look at the response, right? So here we have a Grignard reagent and we're given the product. So the same thing I was talking about earlier. So we're given the product, we need to figure out what happened here. So how do you approach this question? The first thing is that you look to identify the new carbon-carbon bond. So that's why I have been stressing the new carbon-carbon bond, right? So here, and if we just draw this line here, right, that is our new carbon-carbon bond that I just draw the line across, right? So if we know our new carbon-carbon bond, then that will give us insight into what the Grignard reagent reacted with, right? So let me proceed to the answer. All right, so if you drew this aldehyde, then you'd have gotten it right, right? So let's count our carbons for a second. So we have, let's say our methyl is 1, and let's say this carbon is 2, this one is 3, and the carbonyl carbon is 4, right? And let's say we go back to the question, right? And we say, okay, this is 1. What did we label as 2 again? I think this one was 2. This one was 3. And then this one was 4, right? So that's a good idea. So if you now identify that this is the methyl that was added, right, then you are now able to say, okay, I must have a electrophilic center at 4, okay? So that is how you figure it out. Just number your carbons, identify the methyl. You know that it's going to be in the product, so just identify it in the product first. And then after you do that, clearly you'll see the new carbon-carbon bond, right? So then you must know that this center must be electrophilic. And the fact that you have an alcohol at that center, right, that means that you may have had a carbonyl. All right, so here we see our aldehyde, right? So just to mention, let's go back to the question again. We're not seeing the hydrogen, right? Because I deliberately chose these line angle diagrams so that you can get some practice with drawing this type of structures, right? So we're not seeing our hydrogen here, but you must know that your hydrogen is present, right? And it's still there. So we have our electrophilic center, which is 4, and we just draw our 2 and our 3. I hope I got the numbers correct, right? So the next step would have been to write out the mechanism, right? So we have our mechanism, and we could have started it differently. We could have shown the generation of the carbanion first. So let me just go ahead and write that out. So if we have the methyl, and pardon my not so elegant writing, right? So if we form the carbanion first, then we would have had this structure here. So you could have done that as well, right? You could have formed your carbanion and then show this reaction here, either from the carbanion to the electrophilic center, and then show that the carbon oxygen bond is broken, and so the arrow starts on the line, ends on the oxygen. So you actually form this complex here, which in the presence of acid displaces the magnesium bromide, right, to form the alcohol, which is what we want to get, right? So the important thing here, what you need to practice is looking at the product and one starting material and being able to figure out what it reacted with, right? It will take some time, it will take some practice, but we have to start from somewhere. All right, so our follow-up question 2 says, suggest reagents and conditions as well as a mechanism for the following reaction, right? So this is similar to what we had earlier. So just try and see what you come up with for this one. All right, so having looked at carbanions, now we're looking at carbocations, which you might be more familiar with, right? So just in case you're wondering again, right, how did they come up with carbocations? Then clearly, we have a cation and it's a carbon. So we have a plus charge and a carbon. So for short, we call it carbocation. So that's what we're looking at now. All right, so as we did with carbanions, we're looking at the structure and geometry of carbocations, right? So the carbon atom bearing the positive charge in this case is sp2 hybridized. Therefore, the ion is trigonal planar, so different geometry from the carbanion. And in a similar fashion, we're looking at how they are generated. So they are generated by heterolytic fission or by electrophilic attack on a neutral molecule or from other cations. So here we're looking at all three. So the first is the heterolytic fission or dissociation, right? So here we see the opposite of the carbanion, right? I hope you're thinking like that, because with the carbanion we went this way, and with the carbocation we go the other way, right? So the pair of electrons will now reside on the halide in this case, right? And so clearly whatever carbocation that will be generated must be a stable one, right? So if you recall from, preliminary chemistry, if we have a tertiary carbocation, then that is stable and favorable. And of course, if we have a polar solvent, all the better for generating this carbocation, right? So this is the first way, heterolytic fission. The second way is via electrophilic attack on neutral molecules, right? So here we have an alkene, right? Alkene double bond. And if we show here that the arrow starts on the double bond, right? And it ends on the acid, right? So clearly we have two bonds here. And so one of the bonds will break, and so it will generate a carbocation, right? And just some other examples here where we have an alcohol, right? So it is protonated, and now we have a good leaving group in the form of water. And so this carbon-oxygen bond can break easily to quench positive charge and to form a very stable carbocation here. And as you would have seen with electrophilic aromatic substitution, the benzene ring would have started that reaction, and we have our electrophile here, and the benzene ring here is being nucleophilic, who will attack our nitro group, and we have substitution of our hydrogen eventually with the nitro group here. But we're showing the formation of the carbocation here, or in this case the arenium ion. So when you have a plus charge on what was a benzene ring, we call it an arenium ion. All right, so here we see three ways of electrophilic attack on neutral molecules. So the neutral molecules being the benzene, the alkene, as well as this alcohol here, right? So note here that we always want to form a very stable carbocation, right? This one is very stable. The arenium ion is very stable, stabilized by resonance. And this, if we have here, we have the option of the carbocation forming on this carbon versus this one. And of course, the reaction will favor the more stable secondary carbocation seen here. And then finally, the generation from other cations, right? So we have the reaction here where we see, an amine, primary amine forming a diazonium ion. This is a very temperature sensitive reaction, right? So the salt here, the aryl diazonium salt, is stable between 0 and 5 degrees. And so, it will spontaneously decompose to form nitrogen gas and the carbocation, right? So again, we have our amine form our diazonium salt that is very unstable. And so this alkyl or aryl nitrogen bond here will be broken, as is evidenced by the arrow starting on the line and ending on the nitrogen, quenching the positive charge and liberating nitrogen gas and or carbocation. So I'm sure this is just revision here, but just to ensure that we're all on the same page. For the stability of carbocation, well, the ease of formation of carbocation is in the following order. So of course, we know that our tertiary carbocations are the most stable of the group here. So the positive charge on the carbon is relieved to some extent through induction by the presence of alkyl substituents. So in other words, the alkyl substituents, because it's tertiary, you have 3 alkyl groups on it. Through induction, it contributes to the stability of the tertiary carbocation. And so heteroatoms containing lone pairs of electrons, so for example, our oxygen and or nitrogen, they can stabilize carbocation via resonance, right? So here, we have our carbocation and we have our resonance arrow here. And we see where we have the electrons, a pair of electrons on the oxygen, forming our double bond here and therefore helping to stabilize our carbocation. As we said before, and that we'll continue to reinforce, is that once we can draw resonance structures, it means that that molecule has increased its stability because the electrons are now delocalized across 1 or 2 or several bonds. All right, so here we're looking at allyl, the allylic cation and the benzylic cation, and they're more stable than most other carbocations. Molecules can form allyl or benzyl carbocations are especially reactive, right? So what is the allyl or benzyl, right? So here we have a carbon-carbon double bond and we have a carbocation here. So an allylic or allyl, right? So we have a carbon that is positively charged, then we have a single bond, then we have a double bond, right? That's all you need to remember. Double, single, and a plus charge on the carbon. So let me go again. Double bond, single bond, plus charge on the carbon. That is our allylic group or allyl, right? And so because this is the case, then the electrons are now stabilized by resonance, because this pair of electrons can now go to form a double bond here, and then we end up with a plus charge on the carbon here, as we see, right? So the electrons are delocalized across these 2 bonds, and therefore again that shows that carbocation has increased its stability. And in a similar fashion here with benzyl, if we have a carbocation here on the carbon that is bonded to the benzene ring, right? So that's why it's benzyl. This carbocation is also resonance stabilized. And you know, if we were to start to draw our resonance structures, we'll draw an arrow from the double bond to form a double bond here, and a plus charge would be generated on this carbon as we see here. And we can draw several resonance structures showing how the electrons can be delocalized across all of these bonds, right? So clearly, once we can draw a number of resonance structures, that carbocation has increased its stability. So systems containing delocalized pi electrons, so alkenes, aromatics, as we have seen, can do this also via resonance, which we just spoke about, right? So that leads us now to question 3, which says carbocations can be generated in 3 ways. What are they? So try to recall, right? So if you recalled, right, by heterolytic fission, that's the first way that we looked at. By electrophilic attack on neutral molecules, and then the third way that we looked at was from other carbocations. You know, we looked at the diazonium ion, right? So what would help you to remember also is to write the examples of these reactions. So our follow-up question 3, right, is saying which carbocation is more stable. So we're looking at the compounds that are in the box, right? So we're comparing this one with this, this with this, this with this, all right? So just go ahead and attempt that question. All right, so as we did with our Carbanion, we're looking here at the reactivity of the carbocation. So what kind of reactions can carbocations undergo? Well, they undergo attack by a nucleophile, right? Loss of a proton from adjacent atom, and also rearrangement to a more stable carbocation, which I'm sure you know all 3 of these already. So these are some examples. So if we have a carbocation, they're susceptible to an attack from a nucleophile, right? So the nucleophile that we have here is methoxide, right? So it can attack our carbocation here to form an ether. Also, you know, another nucleophile is ammonia, right? So from this, we can form a primary amine, right? So the carbocation here can undergo attack from carbocation here can undergo attack from the ammonia, right? And to form our ammonium ion here, which is a nitrogen with a plus charge. So the new bond here is between the nitrogen and the carbon, right? So always keep in mind, what is the new bond? What is the new bond that is formed here? The new bond is between the nitrogen and the carbon. So this carbon and the nitrogen, this carbon was once the carbocation, right? And then once the ammonium ion is formed, a base, we have ammonia here in excess. So ammonia can pull this proton and therefore quench a positive charge by, you know, the arrow starting on the line, ending on the nitrogen, and therefore quenching our positive charge. And we end up with a primary amine. So here we're seeing a carbocation being attacked by another type of nucleophile. Here we see loss of a proton from an adjacent atom to form an alkene, right? So here there's loss of this proton, so this carbon hydrogen bond is broken, and we now have a double bond here quenching the positive charge, and we end up with an alkene, and of course the loss of that hydrogen. And rearrangement, right? So we have seen, you know, various rearrangements before, and the purpose of rearrangement is always to a more stable carbocation, right? So here we have a primary carbocation, and this, we call a hydride shift. So this hydrogen can move 1,2 hydride shift, I should say, because it's 1,2 in relation to the carbon. And so once that hydrogen shifts or moves to the neighboring or adjacent carbon, we now move from a primary carbocation to a secondary carbocation. And so that rearrangement is favored because we're going to a more stable carbocation. All right, so what are we seeing here? Well, if you guessed 1,2 methyl shift, then that would have been accurate. So here we have a primary carbocation again, right? And so the methyl can move to the adjacent carbon, and therefore a carbocation would be generated here, which is now a tertiary carbocation. So can you imagine that movement of the methyl 1,2 methyl shift results in the movement from a primary carbocation to a tertiary carbocation? That is definitely favored because obviously the carbocation, the tertiary one, is more stable. All right, so let's see what happens here. Rearrangement to the tertiary carbocation does not occur because the benzyl carbocation would be more stable due to resonance, right? So this methyl shift, so even though you would have had tertiary carbocation here, right? This does not happen because the benzyl carbocation is more stable, and we already looked at the resonance structures, right? Okay, so that leads us to question 4 now, which says suggest reagents and conditions as well as the mechanism for the following reaction. And if you said, didn't I hear those words already? Well, you did, but for another question. So here we have our alkyl halide and we have our secondary amine. I don't know, something should look familiar to you. And then the first thing that you need to do is to say, wow, I had a substitution between the chlorine and the amine, right? So where the chlorine was, the amine now is. So that's the first thing that you should pick up, right? But what else do I need to effect this reaction, and what is the mechanism? All right, well, let's look at the answer to that. Well, clearly it's a substitution reaction, but what you may not have thought about immediately was, is it SN1 or SN2? Well, if you would have guessed SN1, then that is more likely, seeing that what we would end up with is our substrate is a tertiary alkyl halide, right? And we know those are, the SN1 is more likely for tertiary alkyl halides, right? So the arrow would start on the bond, end on the chlorine to generate our very stable tertiary carbocation, which is now susceptible to attack by nucleophile, in this case ammonia, right? So our ammonia will attack our positive center, right? And to form our ammonium ion, as we have seen already, right? So clearly the electrons, just to say here that once this bond is broken, this carbon chlorine bond is broken, the electrons now reside on the chlorine, which is why we have our chloride ion here, right? And so once the ammonium ion is generated, because we have so much ammonia present, it can pull this proton, and this nitrogen hydrogen bond can be broken, evidenced by the arrow starting on the bond and ending on the nitrogen, right? And so the positive charge is quenched and we form our primary amine, right? So again, the first insight into the reaction is that the chlorine is substituted for our amino group, right? And then the second thing you think of, what is the mechanism based on the substrate, right? So you look at the substrate. I will be generating a very stable tertiary cation here. All right, so our follow-up question 4 is, carbocations can undergo 3 types of reactions. What are they? All right, so the final portion of the lecture here, we're going to be looking at select reactions and preparations of alkenes. So you might be familiar with these methods of preparation of alkanes. That is fractional distillation of crude petroleum, or hydrogenation of alkenes. So you know about, if you have an alkene, right, you can hydrogenate using hydrogen gas and some metal catalyst, right? And then you also have Clemmensen and Wolff-Kishner reductions, as well as from organometallic compounds. So we're going to look at the last 2. All right, so the first is Clemmensen reduction, right? So we're looking at reduction of carbonyl compounds here. So here we have a carbonyl compound, and in the presence of zinc amalgam, and that just means zinc dissolved in mercury, and conch acid, you get an alkane, right? So the reaction is selective for a carbonyl group of an aldehyde or ketone, but does not affect the carbonyl groups of a carboxylic acid. The reduction involves transfer of electrons from metal and protonation of intermediate species. So it's a radical mechanism, but for our purposes, we're not going to go into that radical mechanism. So what you need to know here is the reagents that will effect the reduction of a carbonyl compound to an alkane. All right, so the second reaction we're looking at here is the Wolff-Kishner reduction. So it's a similar reaction of, we have a carbonyl compound and we end up with an alkane, however, different conditions. So the hydrazone of an aldehyde or ketone is prepared and then decomposed under basic conditions. This reduction is preferred for compounds which have acidic sensitive groups, right? So in conditions, when you have groups, aldehydes or ketones, or compounds that have acidic sensitive functional groups, then the Wolff-Kishner reduction is preferred. So the reaction conditions are hydrazine and base and heat, and we get alkane and nitrogen being eliminated. So we're going to go into the mechanism of that reaction. So first, we have formation of the hydrazone, which we see here, right? And we're not going to go into it because we did already when we were looking at investigating reaction mechanisms. And here our group was, we were doing a hydroxylamine, right? So our group was the OA. So we went through this mechanism at length, so you can check that out, right? And so from here, so again, the only difference between that structure and this one is that instead of having the hydroxyl group, we have another amino group, right? So that is the difference. So at the end of the day, we end up with a carbon-nitrogen double bond. I don't know if that rings a bell, but it should ring a bell. At that time, we ended up with a carbon-nitrogen double bond as well, but it was the nitrogen was bonded to a hydroxyl group, as I said before. Hope that rings a bell. All right, so that's the first step, right? So recall the mechanism from previous lectures. The second step, once the hydrazone is formed, is the deprotonation of the hydrazone, right? So recall that we have a base, right? We have potassium hydroxide in the reagent. So the base can pull this proton, right? And then causing the nitrogen-hydrogen bond to break, and then the pair of electrons now reside on the nitrogen, as we see here. That intermediate is resonance stabilized, right? So we can have, if we were to draw our arrow, it would start on the nitrogen, end on our bond here to form our double bond, and then the other arrow would start here and end on this carbon, which is why we have a negatively charged carbon here and the nitrogen-nitrogen double bond, right? So once this resonance structure is formed, then this carbanion can pull a proton from water, right? So that is the next step. So under strong basic conditions, as we said before, the hydrazone is deprotonated at the nitrogen atom. Delocalization of the negative charge forms a more stable carbanion, right? So this carbanion is more stable than this anion. A negatively charged carbon is more basic than a negatively charged nitrogen. Nitrogen is more electronegative, right? So our third step involves the loss of nitrogen, right? So again, the base will pull the other proton, form the negative charge that we see here, and then this negative charge would form nitrogen, which is liberated, breaking this carbon-nitrogen bond to form a carbanion, right? So we form another carbanion here. So the nitrogen is deprotonated, as we said, that happens in this step here. This allows for the loss of nitrogen, which is a good leaving group, and we have seen that when we were looking at the formation of carbocation, right? So that nitrogen is a good leaving group. This results in the formation of another carbanion. The fact that we have the pair of electrons now residing on the carbon suggests that we have a carbanion. So once that carbanion is formed, it can pull a proton from water, right? And then this hydrogen-oxygen bond is broken, and now the electrons now reside on the oxygen to form our alkane, right? So, you know, it might seem long, but I'm sure when you actually write it out yourself, it won't seem as long, and some of the steps kind of repeat themselves, so you'll get the hang of it. All right, so just try to write out the steps a number of times so that you can get it solidified in your mind. So protonation of the carbanion results in the formation of the alkene, as we said, right? So the second way in which we can form alkanes is via organometallic compounds. All right, so again, you're familiar with Grignard reagents. So Grignard reagents can be easily protonated to form alkanes. They are strong bases and will not add to carboxylic acids, as we see here. Right, so we have our Grignard reagents, and this is deuterium, yes, and basically it will be protonated, right? So that's another way in which our alkenes can be formed. So we have our Grignard reagents here again, which, well, reagent here, which can be protonated to form an alkane, right? So we're seeing it twice here. Another reagent or another organometallic reagent is Gilman reagents, and you might know it as an organocuprate. And as we mentioned before, you know, two alkyl groups, copper and lithium. So the coupling of an alkyl halide with a lithium dialkyl cuprate results in the formation of a carbon-carbon bond, right? So Gilman reagents are effective nucleophiles for SN2 reactions. All right, so here we have our lithium dialkyl cuprate, right, in the presence of an alkyl halide, primary or secondary. Secondary cycloalkyl halide, we can have formation of a carbon-carbon bond. So notice that the carbon-carbon bond is between the alkyl of the alkyl halide and one of the alkyl on the lithium dialkyl cuprate, right? So that is a new carbon-carbon bond that is being formed. So for the synthesis of these lithium dialkyl cuprates or Gilman reagent, it starts off with the formation of a organolithium, right? So the alkyl halide in presence of two equivalents of lithium forms or organolithium compound. Step 2 is a formation of our organocuprate or Gilman reagent. So in the presence of copper bromide, and we can also use copper chloride or iodide, and the organolithium that was created in step 1, you form our lithium dialkyl cuprate. So just to reinforce here that the R2, when we say that it's a R2, well, 1, this is a structure, and 1, 2, 3, 4 carbon on this side, 1, 2, 3, 4 carbon on this side. So it's the same R group twice on the lithium dialkyl cuprate. And just to reinforce here that the new bond is now formed between this alkyl halide and one of the R groups to form the new carbon-carbon bond. All right, so just to do a comparative between Grignard reagents and Gilman reagents, well, Grignard reagents don't work well for SN2 reactions. Shocker, right? So if we have an alkyl halide and we have a Grignard reagent, there will be no SN2 reaction because you have competing reactions, deprotonation, reduction, etc. However, for Gilman reagents, they're effective for this reaction. So our lithium dialkyl cuprate will form a carbon-carbon bond here. So if we count our carbons, right, this is 1, 2, 3, 4, and our lithium dialkyl cuprate, as we said before, we're only transferring one of the alkyl group. So in essence, we should have 4 plus 2, 6 carbons here. So let's go. 1, 2, 3, 4, 5, 6. So 6 carbons in total. The new bond, however, is here, right? So here for the alkyl halide and here from the lithium dialkyl cuprate. So a successful SN2 reaction. So what we're saying here is that the Grignard, it won't happen if we use Grignard reagent, but it will happen if we use Gilman reagent. So you need to know the difference. Another difference here is reaction to carbonyl compounds such as ketone, right? So a Grignard will add to it, and then after acid workup, you know, one of the questions that I asked earlier had a similar reaction, right? So we'll form a alcohol if we have a Grignard reagent, which we call 1,2 addition. However, for the Gilman reagent or the lithium organocuprates, right, It doesn't. There is absolutely no reaction when you react a carbonyl with a lithium dialkyl cuprate, right? So just to point out here that for Grignard, right, for this reaction, the Grignard no SN2, the Gilman will form the carbon-carbon bond. Here it's the reverse. The Gilman no reaction with carbonyl compounds. However, Grignards react with carbonyl compounds. So for reactions of alkanes, right? Alkanes, as we know, they possess covalent non-polar bonds, so they are therefore inert to most chemical reactions. They do not react with most acids, bases, or reducing agents. They, however, react in the presence of a flame spark, heat, or high intensity light source. So you can have combustion or free radical halogenation, which, I mean, you would have been familiar with these two already, right? So for the free radical halogenation, again, you have your initiation step, your propagation, and your termination. So an initiation step involves, and notice that these are all half arrows, right, which shows the movement of a single electron, which is why it's a free radical halogenation. So one electron will go here, the other one will go here to form two radicals, and that is our initiation in the presence of light or heat, right? Our propagation step involves the reaction of a radical with a neutral molecule, and we have two examples of a propagation step here. And our termination steps, they involve the combination of two radicals to form a neutral molecule, right? So here we have our chloromethane or carbon-carbon bond here, and we have chlorine being formed again here, right? So these are our termination steps, right? So an alkane can react, and this is the simplest alkane here, methane, can react with a radical halogen to form, you know, either chloromethane or methane, seen here, or other combinations, because you know the nature of free radical reactions. And for the energy profile of the free radical halogenation, we start off with our radical and our methane. We end up with our intermediate, and we have propagation step 1, propagation step 2. So clearly we have our transition state here in which our carbon-hydrogen bond was being broken. And here we have our second transition state, where you had formation of the bond between the carbon and the chlorine to form the product, right? So we have our radical intermediate here, and we have our starting propagation step 1, propagation step 2, leading to our chloromethane here. All right, so this leads us now to our final question, which is determine whether there could be a Gilman or Grignard reaction based on the nature of the substrates. So we're looking at the fact that we have a carbonyl here. So guys, let's try to answer the question before you see the next slide, right? So here we have a carbonyl, and here we have a primary alkyl halide. The question is, which reaction would happen? Would we have a reaction with a Gilman reagent or a Grignard reagent? So if you guessed Grignard for the first, that is the carbonyl, and Gilman for the second, which is the alkyl halide SN2, then you would have had the answer and you're learning. All right, so our final follow-up question is question 5. Suggest reagents and conditions as well as mechanism for the following reaction. So go at it, attempt it until we meet. All right. So thank you so much for watching. Thank you for making it thus far, and see you next time.